Today, we're diving into a huge question, one that scientists and philosophers have been wrestling with for ages. How do we actually build a complete picture of reality when, let's face it, each of us is only holding a tiny piece of the puzzle? This is a problem that stretches all the way from ancient thought experiments right to the cutting edge of AI and physics.
I mean, think about it. It's one of the most fundamental challenges there is. You have your unique viewpoint, I have mine, and we've both got our own set of data. So how on earth can we stitch all those different fragments together to create something that looks a little more like, well, the truth? That's the core question we're going to get into today.
You've probably heard the old story, right? A few people who can't see are trying to figure out what an elephant is. One touches the leg and says, "Oh, it's a tree." Another feels the trunk and is convinced it's a snake. The thing is, each person's perspective is technically true, but it's also completely incomplete. This ancient problem is exactly what modern science is now trying to solve, but with really powerful, formal, computational tools. Okay, so before we can build a solution, we have to look at the foundations. And this isn't some new problem that just popped up with technology. Philosophers and quantum physicists have been grappling with the nature of perspective for a long, long time, and their ideas are really the bedrock for all the models we're building today. This quote from computer scientist Kai-Yu Wan just nails it. A context is really just a fancy word for a perspective, and by its very definition, it's partial. The only way you can even get close to a complete description of reality is to somehow gather and integrate all the different contexts. But that's the big question, isn't it? How do you actually do that in a structured way? Now, you might not expect this, but one of the most powerful toolkits actually comes from quantum mechanics. I mean, for decades, physicists have been tearing their hair out over how different observers can measure things that seem totally contradictory, and yet they're both right. The whole struggle to coordinate those individual perspectives into one coherent framework is a central theme of the entire field. There's this fascinating theory called relational quantum mechanics, and it suggests that facts aren't absolutes. They're actually relative to whoever is observing them. But, and this is the really important part, when two observers interact, they can create what are called cross-perspective links. Just think of it like two people comparing notes. Before they talk, they each have their own story. But after they talk, they've created a new, shared reality based on their combined information. And, of course, it isn't just quantum physics. There's a whole landscape of ideas feeding into this. You've got philosophical concepts like Nietzsche's perspectivism, the idea that there are no absolute facts, just interpretations. Then you have mathematical frameworks like situation theory, which tries to formally model context itself. All of these different fields are providing the raw ingredients for the computational tools we're building now. So with all that philosophical groundwork laid, let's actually open up the toolbox. We're going to take a look at some of the really powerful computational and mathematical frameworks that scientists are using to turn this abstract idea of summing up perspectives into something practical. First up is a field with a pretty big name, computational phenomenology. But the goal here is, well, incredibly ambitious. It's trying to create a mathematical model of subjective experience itself. It's basically an attempt to build a bridge between how someone feels on the inside and the hard data we can measure on the outside. Next up is category theory. Now, this is some seriously abstract math, but the core idea is incredibly powerful. The best way to think about it is as a set of rules for combining a bunch of different maps into one giant, perfectly consistent world atlas. It gives us a formal blueprint for how a group of people, each with their own little map of reality, can merge them into a single shared understanding without any contradictions. What's really cool about the hypernetwork model is how simple and elegant it is. It looks at all the complicated stuff in a system, physical boundaries, social hierarchies, different points of view, and it just says, you know what? Let's just call all of these relationships. By boiling everything down to this one common element, it makes the job of integrating them way, way easier. And finally, we've got multi-scale modeling. This one is absolutely essential for understanding really complex systems, like our climate or an economy, or even the human brain. It's all about integrating perspectives from totally different scales, from the microscopic to the macroscopic, from what happens in milliseconds to what happens over years, to build one single unified model that works across all of them. So just to do a quick recap of our toolbox, we've got tools to model an individual's inner feelings, tools to figure out how a group creates a shared belief system, and tools to simplify really complex systems by finding a common language. Each one gives us a different angle for tackling that classic blind man and the elephant problem. Okay, I know this all might seem incredibly abstract, but these frameworks are actually being used right now to solve some very real-world problems. So let's take a look at how they work in practice. This is a perfect example: cybersecurity. Instead of just relying on one analyst's gut feeling, a system can collect the viewpoints from many different analysts at once. It then formalizes all that knowledge, automatically flags where their stories conflict or where there are gaps, and then synthesizes it all into one unified picture of a potential threat. It's literally the blind men and the elephant problem, but for stopping cyber attacks. And the applications are just so broad. Researchers are using these models to understand how an entire culture's worldview, which is just a massive shared perspective, comes to be and why it stays so stable. And in AI, these frameworks are helping us to find different kinds of creativity. For example, large language models are amazing at what's called combinatorial creativity. They basically take the millions of perspectives in their training data and find incredible new ways to recombine them into something that feels new. And that brings us to our final and maybe the most exciting frontier of all, using these frameworks not just to model the world, but to model how we think about the world together. There's this amazing idea called the symbolic mirroring framework. Imagine building an AI that acts like a perfect mirror during a group discussion. It doesn't just reflect back one person's opinion. It collects and unifies all the different, even conflicting viewpoints. The final image it shows back to the group isn't any single person's idea, but a brand new, higher-level synthesis of the entire group's shared thinking. Now, this is actually something we humans do all the time without even thinking about it. It's called imagined deliberation. When you're facing a tough decision, you often mentally simulate how different people you know would react. You literally play out the conversation in your head. AI models are now being designed to do the exact same thing, just in a much more structured and massively scalable way. The really crucial difference here is how you set up that simulated conversation. You could have each perspective work in its own little silo, kind of like people brainstorming in separate rooms. That can be pretty inefficient. A much more powerful approach, which you see on the right, is integrated deliberation. That's where everyone is in the same room, adjusting their own ideas in real time as they hear what others are saying. It helps the whole system find the best solution way, way faster. And you can actually control this with precision. These models have something called an influence parameter. Think of it like a dial. You can turn it all the way down to 0 and all the simulated agents think independently. Or you can crank it way up, making them super responsive to each other. It lets you fine-tune the exact nature of their collaboration. Which leaves us with one final and pretty mind-bending question. We started with the idea that our own human perspective is always incomplete. But what happens when we build a machine that can formally integrate thousands or even millions of perspectives all at once? When a machine can finally see the whole elephant, what new realities, what profound truths will it see that have always been invisible to us? Thanks for tuning in.